Good morning, everyone. Welcome to the final lecture in the tectonics course. In continuing our series of case studies of interesting tectonic settings of the world, I'm going to talk today briefly about the Apennines. This is an example of what we call a retreating subduction zone where the slab is rolling back, leading to upper plate extension. So this is Italy. I'm going to be talking about the sort of the entire Apennine chain, which runs the entire length of the peninsula of Italy, but much of the focus will be up here in the northern part for reasons which I'll explain later in the lecture. So Italy, the Apennines and the subduction system here are an example of what we call a retreating subduction zone, which really has to do with the kinematics of the two plates. So subduction is defined by one plate going under the other plate, but the upper plate in these settings can deform. And it can deform either in contraction, that is shortening under convergence, or in extension, which is like this. And we think that the dynamics of this process is linked to the motion of the slab, and in particular, the motion of the slab with respect to the upper plate. There's also motion of the slab with respect to the underlying mantle, so the whole system is sort of a coupled geodynamic system. But if that slab is advancing towards the interior of the plate, that's going to lead to shortening in the upper plate and a sort of Andean type origin. If the slab is retreating away from the center of the upper plate, that can lead to extension of the upper plate. In the oceanic setting, we recognize that then as the cause of back arc spreading and the formation of a back arc basin. In a continental setting, this is a little more complicated, and that's what we'll be looking at today with the Apennines, because the upper plate is continental crust. So these ideas of sinking or retreat or rollback of the slab go back to the early days of plate tectonics. In particular, it was recognized that a slab being heavier than the surrounding mantle is going to sink. And that sinking motion, even if it's sinking directly straight down into the mantle, that leads to a retreat of the hinge, or what was called originally by Belsasser in this early paper as retrograde motion of the slab. The hinge, that is the sort of the center point where the slab goes from some dip angle to horizontal, is going to retreat back in this direction from left to right in this picture. And that happens even if the slab is just sinking directly down, because the point that's up here in the upper part cannot sink directly down. So this hinge, in order to accommodate that motion, is going to have to retreat back to the right in this picture. The forces underlying this are not so clear. This is say linked somehow to the mantle flow. If the mantle flow is sort of the way we imagine it occurs in this plane, sort of a corner flow like this, this can help to drive that slab backward. In addition to this retrograde motion, if the upper plate can't move, that can lead eventually to failure and extension of the system here. It could also be related, though, to far field forces, for example, in the upper plate. If there's something that's pulling on the upper plate in this direction, for example, if this is going into another subduction system over here, so we have slab pull operating on this plate, that can also lead to a tensional state of stress and eventually failure. This failure point, either here or here, we think is often linked to the arc volcanism, which tends to weaken the plate through its thermal effects. So the Apennines and Italy are an example of this kind of process. I'm going to show you a bit of some of the reconstruction of where this subduction system has been back through time, but this is a quick summary of that already. The modern subduction system, the trench is located, or the deformation front is located along the white line here today. So this is the leading edge of the deformation of the upper plate. Subduction is down to the west of the Adriatic Ocean here. But as I'll show you in a moment, we can reconstruct where this trench or deformation front was back in time. And this is that position in millions of years, going back to about 35 million years. So what we can see is that it has in fact been retreating across the Mediterranean, closing the Adriatic Ocean, which was originally much, much larger than the relatively narrow ocean we see today. So if we put that into the modern tectonic setting or context here, here's the tectonics of the Apennines, or of the entire Mediterranean. There's a series of relatively small subduction zones or convergence systems south of Anatolia. So if you can locate yourself here, Black Sea, this is Turkey and Anatolia here. South of Anatolia, then we have the Cyprus subduction system that goes into the Aegean Sea. This is all a down to the north subduction system. Then we have the Apenninic system, which is a down to the west system, and the Dinaride system, which is actually a down to the east system. This one is less or not active today, at least in the northern part, but is an important orogenic belt that also involves subduction. We have another, which is really a subduction system that goes all the way up through the Carpathians and connects up into the Alpine system. So this is the one that we recognize as subducting Europe underneath the Adriatic plate, or the southern complex of tectonic regions in here, and the Carpathians is part of that system as well. Over to the further to the west, we also have at least old subduction systems along North Africa, and quite an active subduction system then over underneath Gibraltar out into the Atlantic system here. Earthquakes in the area show the same pattern. These are really focused on the active subduction systems. The Aegean is clearly the most active system. Aegean Cyprus, south of Turkey, is the most active system. These sort of trickle up into the Dinarides then. But the next most active is probably the Apennines. And these are the earthquakes that are occurring right along the center of the Apennine mountain belt, along here down into Sicily in this area here. And we can see again also the Gibraltar system and so on over here, trickle of earthquakes up into the Alpine region, and the southernmost Carpathians are still seismically active. We think this is sort of the last stage of deformation of this subduction system that once underlay the Carpathians. We can also see this in the geodesy. These are the GPS velocities for the Mediterranean region. This is in a European reference frame. So this is the velocity of individual points then relative to stable Europe, say somewhere up in the north here. We see this big motion of Anatolia to the west, and then down to the southwest here. This is again the Aegean and the arc and the back arc region of the Aegean subduction system. So this is kind of interesting because the subduction here is down to the north, right? This is subduction of the Mediterranean down to the north underneath the Aegean, but the Aegean itself, or the arc and the forearc parts of the Aegean, are moving to the south. So the subduction to the north, the motion to the south. This is another example of one of these rollback or retreating subduction systems where the arc and the forearc are moving in the direction opposite to the subduction. And that implies extension in this region, and the Aegean, of course, is well known for its extensional structures. The Apennines are a smaller version of this. The motion of the Italian peninsula is dominantly to the northeast relative to Europe. That means that there is convergence across this zone, and I'll show that again a little bit better in another slide, but there's convergence in this region, which is really representing the subduction. But there is no motion of, say, Corsica, Sardinia with respect to Europe. There are stations here, and those stations are simply not moving with respect to Europe, so there's no arrows shown here. But that means that there is extension going on between this point, or this mountain range, really the whole of Italy, with respect to Corsica and Sardinia. So if we go back into geological history and have a look at this system and how it evolved, this is looking back now at 35 million years ago. At this point, there was no Italian peninsula. This is what will become the Adriatic, and Italy is sitting right here, the Apenninic system. This is all ocean at this time. So this is, excuse me, this is all one single ocean basin out here. We had subduction along the boundary here, which is the Dinaritic system. We had subduction in the Alpine system. This is really kind of the early stages of collision of the Alpine system. So we did have some continental crust up here in this region. We had subduction down underneath Iberia and the south of France in this region here. This, particularly this system, also the Dinaritic system a little bit, but primarily this subduction system had extension in the back arc associated with it. And that's right here, for example. So this is opening up what's going to become the Provençal Basin, which is the western part of the Mediterranean now. You can see here Corsica and Sardinia lying on their sides, and we have extension between France and Spain and Corsica and Sardinia. This is eventually going to open up into the Provençal Basin. And we see this now if we jump forward to about 23 million years ago. In particular, looking at this again, at this area, the subduction zone is now starting to retreat away from the continent as we open up these extensional basins here in the Western Mediterranean. At 15 million years ago, we have even more well-developed extension now. This is really the Provençal Basin now, has now fully formed. In fact, this is almost the end of the extension in this area. So Corsica and Sardinia are now pretty much in their modern positions with respect to Europe. The subduction has moved off to the east, and there's another system here, at least in this interpretation, that's now to the south and moving to the south, which is again opening up this part of the Western Mediterranean. Notice just another areas out of interest, for example, the Pannonian Basin. Pannonian Basin is also an extensional basin. So this is the Carpathian subduction. This would actually connect up again into the Alpine system, which is just kind of not emphasized here, but this would have been the Alpine collision subduction all the way across through the Carpathians. But in the eastern Carpathian part of the Alpine system, the slab must be rolling back, and we're having a little bit of extension of the upper plate, and that's forming in the Pannonian Basin, which is an extensional tectonic structure. 10 million years ago, again, let's go away from the Apennines for a moment. The Carpathians are developing well. We have, in fact, marine rocks that are here because of the pulling down of the slab here, opening of the Pannonian Basin. The Aegean system is now starting to develop pretty well. So we have subduction along the Aegean system here with extension, again, back arc type extension in the Aegean and in westernmost Anatolia. But if we jump back to the Apenninic system, we see again that we have now fully formed the Albaran. Well, we started forming the Albaran Basin and the Algerian Basin, but the Provençal Basin is now fully formed. The trench has migrated further to the east, and we've now actually started to form extension between Sardinia and Corsica and what will become the Italian peninsula and the Apennines. So the extension has sort of jumped from this basin across Corsica, Sardinia into what's going to now become the Ligurian Tyrrhenian Sea here. 5 million years ago, we've seen more of that. The trench has migrated further east. The extension is now focused in this region. And if we go to the present, we have now the current position of the trench along here, wrapping around the entire peninsula. We have now an extensional basin, which is the Tyrrhenian Basin now particularly between southern Italy and Sardinia, but it's sort of a smaller basin that's between Corsica and northern Italy in here. The other systems, the Carpathians are largely finished. The Pannonian Basin has now stopped extending. This last little bit of the subducting slab. There's just a little corner of it left here where we had those earthquakes, if you recall, and then the Aegean system, which remains pretty active down here in the south. So again, the picture, we'll go back to this picture to show that the modern trench is here, but we have this history then of migration of that trench and the whole orogenic system across the Western Mediterranean over the last 35 million years. If we look at some of the other characteristics of the Apennines, this is the crustal structure, for example. This is the crustal thickness now. Depth to moho is being mapped here. You can see Italy somewhere back in here is the very fine line back here. Adriatic is over here. What we see is that there's a thickening of the crust as we go under the Apennines, and then there's this abrupt boundary here along this black line here and relatively thinner crust in this region. Now, the reason that there's such a sharp line is because this is really two different mohos, because we have two different plates. This is a plate boundary along here. So in fact, the Adriatic crust is subducting down underneath the Apennines and it's going under the crust here. So we're really looking at two separate plates. This is the upper plate, or the Tyrrhenian plate, if you want to call it that. This is the Adriatic plate. And so this abrupt boundary is really not really a wall in the crust, but it's just showing where this crust is disappearing underneath this crust. You see the same pattern in the Alps. Up here, for example, we have the very thick crust as the or large depth to Moho, where Europe is being subducted down underneath the Adriatic plate here and relatively thin above it in the Adriatic. Seismicity, if we look at the earthquakes, focusing in now a little bit closer than that first map I showed, looking at really north central Italy up into the Alpine region up in here. We see that there's a very clear band of seismicity, very active. These are the destructive earthquakes that we read about in the news periodically in Italy. It's certainly one of the most hazardous parts of Europe for earthquakes. These are really following then this crest of the mountains and the boundary. Remember, the deformation front is actually offshore here. So the subduction system starts somewhere out here. These earthquakes are directly underneath then the contact between the two plates or within the upper plate. Some of them are actually within the lower plate. This we can see a bit by looking at the depth and type of earthquake as well. So in particular, if we look at this at the right side here, these are the focal mechanisms for the earthquakes in the depth of 10 to 30 kilometers. So these are relatively deep earthquakes. These are the ones that would be either on the subduction interface or in the, mostly in the lower plate, some of them in the upper plate at 10 kilometers, you might be in the upper plate back here. But a lot of what we're seeing now is really the seismicity of the lower plate in the interface. And this we can see by looking at the focal mechanisms here, where these are color-coded to make them easier. So if you're not familiar with looking at these sorts of focal mechanisms, in this case, the blue are thrust events and the red are normal fault events. So compression and extension, if you want to think of it in that term. But what we see is that all of these thrust events along here are located down along the interface or in the lower plate. So we're seeing really the subduction, compression, contraction, slip along that subduction interface in these earthquakes. In contrast, the ones that are more inland, even at these depths, 10 to 30 kilometers, tend to be normal faults. And this is even more clear if we look at this, which is the shallow earthquakes. This is 0 to 10 kilometers now. And we see that most of these are occurring in the upper plate now, right along the crest of the mountains. And these are almost all normal faults. So we're really seeing extension of the upper plate, really very close to the trench, right? I'll show you some cross sections in a moment. We'll see just how close to the contraction in the trench this really is. But the upper plate is undergoing extension. The deeper system plate interface, lower plate, is undergoing compression. This is sort of consistent with the GPS. It showed the regional map earlier, but here's a zoom into the Italian system. So lying on its side, Italy lying on its side, the black arrows are the observations. So this is the observed direction of motion with respect to Europe again. We have, again, this sort of eastern, northeastern dominant direction of motion for most of the peninsula, except that we have no motion at all once we get over to some of the islands over here, North Africa or Sardinia, Corsica, no motion with respect to Europe. So that means that if these are moving, if this part of the system is moving northeast and this is not moving at all, we have extension in this region, and this is what the blue arrows are sort of indicating. This is a region of extension, and the complement is over on the northern or the eastern side here, where we have relative motion implying contraction, and that's what's indicated by the red arrows here. So compression, contraction along this boundary, and immediately into this region, we go then into extension. So we can see this also in the structures. Oops, I've lost one figure. Excuse me, I'm going to pause this for a second and try to fix my picture here. Okay, I'm back. We can see my slides better now. So what I want to show here is something about the structure and the deformation, particularly along the deformation front. So this is either the trench, but we really would refer to this more as a deformation front because it's a continental orogenic belt. But if we zoom in on this area, this is again now in the northern Apennines. This is the Po Plain, so this is the foreland of this system. But in fact, these thrusts go quite far out into the foreland, as you see the deformation front here. And that's this sort of location map of the cross section that's above here, this AA prime. The mountain front here is right kind of following along. Actually, it's inside from Bologna, Modena. It's really following this line along here. But there are these thrust faults that are actually underlying the Po Plain sediments. And we see that here. And what we can see in these structures is, again, the topography here is essentially zero. This is topography. You see the Q here is quaternary fill. So this is full of sediments. So the topography shows almost nothing. It's pretty much flat. But underlying this, we have this whole series of thrust faults along here. And we're seeing that this looks like our classic sort of fold and thrust belt with a whole series of thrusts. This is vertically exaggerated, of course, they're not so steep, but this is showing then this whole series of thrusts that are propagating out into the foreland here. It's then overlaying with sediments until we get back to here, where we then have the first thrusts that are bringing up topography and building the mountain belt really back here on the border along here again. All right. So this is sort of our classic fold and thrust belt. This is, our orogenic wedge, accretionary wedge, whatever you'd like to call it, but it's really showing that this is a region that's undergoing contraction. And if we look at the things like the very young sediments that are overlying these, many of these structures are active today. We see that through the deformation of the youngest sediment overlying them. So another picture of this, again, this is the geological map showing the various units that are now being brought up into in the orogenic belt. And I can say a little something about those later. But the important point is that these are exposed because we have topography and erosion going on here. So this is, again, the mountain belt. We're going here from Florence, Bologna, over to Genova. So the northern Apennines, where we're uplifting the mountains, eroding and exposing the deeper parts of the orogenic belt here. But out here in the front, we then go into the foreland basin, and the actual deformation front is way out here. And this is now the buried front. So we have what's the classic foreland orogenic belt relationship, where we have a wedge top depot zone here where we're getting deposition on top. So again, another cross section of this showing the fold and thrust belt here. Now we're going from the front will be out here somewhere. This might even be the frontal structure here, but we have then this whole series of thrust faults, little anticlines and structures out buried underneath the sediments. We come up to the mountain front somewhere about here, and we can start to see this stuff. But then the deeper rocks being exposed with no sediments on top here. So but the other feature here that's interesting is these red faults. So the black are all thrust faults. These red faults are normal faults. So these, and many of these are in fact cross-cutting the thrust faults. You see here, for example, there's a thrust fault here, but a normal fault is cross-cutting it here. This is now the extension zone. So in fact, as soon as we get into the mountains, really here, we're starting to see active normal faults. And these normal faults are younger than the thrust faults based on things like these cross-cutting relationships. So the pattern that we're seeing here is really one of thrusting in the front. But as that thrust belt propagates outward, the mountain belt is growing, our usual sort of accretionary wedge growing structures. It very quickly goes into extension. And that's these structures back here. And so we, in fact, arguably, if we looked carefully at the earthquakes, we would find that these normal faults, which are active, in some cases are directly overlying active thrust faults. And of course, the subduction is continuing down here. So this region, it's not only the frontal region that's under compression, but also this deeper region here is under compression. The extension is shallow and limited then to the upper plate, the back parts of the system, or the very shallow parts of the system. Just a couple words on the geology here then, and what these units are that we're looking at. The green up in here is older melange structures, or older accretionary wedge structures, and the marine sediments. This is sort of Eocene in age. That's what we refer to as the Ligurian Nappe system. This is really this old marine system that was incorporated into the into the accretionary wedge in the early collisional stages, and it's then sort of ridden across the entire Mediterranean as other material was accreted into the front or underneath it. And that's this unit here, for example. This is a kind of structural lid, if you want to refer to it in that terms. Old, it's even got ophiolites in it, so it's clearly a marine accretionary wedge system. In front and partially underlying this are these brown units here. These are foreland basin sediments. Pretty much all of these brown, orange, peachy colors, that's these ones in here. These are all essentially molasse type deposits that were deposited out here in front of the orogenic system originally, and they've been carried in then by the subduction and accreted as naps and thrust sheets, either underneath this older material, like along here, or out in the front in a series of frontal thrust systems. And there's a little bit of what's sort of interesting then are these yellow sediments here. These are younger. These are Pliocene. Most of these are Miocene to present. We were out in here, it'd be going all the way to the Quaternary stuff. So this is the modern foreland system. This is the older foreland system. But we also have these Pliocene basins that are sitting all through the system here. These are kind of little piggyback basin like they're shown here. These are things that are where the sediment was deposited during the deformation, during the thrust deformation like this. So the equivalent would be things like the purple stuff out here. It's deposited on top of, say, a synclinal structure we would have here, for example, and then that whole system is carried into the mountain belt. So to take a little step back and look at a little larger scale, we can see this whole system again. Here's the subduction system. Now we're going all the way down to moho depth. So we're looking at sort of a larger view of this. This is a little somewhat idealized, but this would again be sort of more in the southern part of the system, perhaps. But here now we can see this contractional orogenic system here. Here's looking again at the front of that system. And then we have behind this extensional system with these sort of cross-cutting later features. You can again here see these red faults or all these normal faults that are cutting across the orogenic belt. And you're cross-cutting these contractional structures. So we can see these extensional structures on land quite well because they are really right along the crest of the mountain range. So again, in map view here, the red are thrust systems and the yellow are normal faults. So we're seeing the yellow structures cross-cutting these red structures. We see that in seismic data, like down here. This is a big normal fault system. Both of these red lines here are big fault systems that are cross-cutting all of these older structures. It's dropping down this block with respect to this. We can see that in the geomorphology. This is a little graben. This is a little extensional basin. We're up in the highest part of the Apennines, the central Apennines. We have relatively big mountains, but we have in the middle of the mountains, we have these big flat-lying basins. And these are forming in response to motion on normal faults that are bounding the basins here, forming either half grabens like something in here. This, for example, Val Tiberina is one of these little half grabens that would be down dropped here. It ends up collecting sediments, and we end up with these little high basins in the middle of the mountain belts. You can see along here this little snow line along here. This is a normal fault, and that's actually the fault scarp. It's collecting snow in this case, but if you were to see this this is summertime probably, or early summer, but this is there's a little bit of down drop then on this side of the system, forms a fault scarp, and it's in this case collecting snow, but this is an active normal fault. What about the geomorphology? We can look a little bit just quickly at the geomorphology. First of all, if we look at the mountain belt in general and compare it, for example, to the Alps. Here's a cross-section across the Apennines and a cross-section across the Alps. The Alps are in blue, the Apennines are in red here. And what you can see is that these are the topography is very subdued compared to the Alps. So the Apenninic system, is really one to 2 kilometers is sort of the high point of the system, whereas the Alps, of course, go up more like 3 to 4 kilometers on average for sort of peak elevations. So the topography is very much subdued compared to, say, the collisional system of the Alps. Now, the reason for this is probably twofold. It's first of all, there's less deformation. There's less deep crustal deformation. The Alps is bringing up relatively deep crustal rocks. We see this in the metamorphic, high-grade metamorphic rocks we find in the Alps, whereas the Apennines has only very limited exposure of rocks that are coming up from, say, mid-crustal depths, but it's mostly a shallower shortening of the upper crust. But the other reason is that this is still, the Apennines has this deep slab hanging underneath it, and that slab is isostatically suppressing a lot of the topography. So it's really the weight of the Adriatic slab, which is still dangling down here. The fact that it's rolling back indicates that it's heavy and pulling down on the upper plate, and that's going to also subdue the topography, we think, by something close to a kilometer in places. If we look at I'm going to focus in a little bit on the northern Apennines here. For the reason I'll explain in the last slide or two, but the short explanation is this is the part that we think is the most active in terms of the subduction today. The central Apennines is a little bit different, southern Apennines different yet, but the northern Apennines we think is more the sort of classic rollback system where the slab is quite active, and we have all these active thrusts out in the plains here, and active normal faults all through this region. So if we look at some of the topography, again, zoom in, here's 4 cross sections you can look at across here. This is so northeast to southwest. Again, we're going up to just 1.5 kilometers, no more than sort of 2 kilometers in the northern Apennines. But we do have this sort of wedge-like structure, right? If we were to look for a taper angle, we could calculate a taper angle along here, consistent then with the thrust belt that we're seeing along here. Steeper on the backside, so this would be our retro wedge to the system, would be on this side of the system, and the pro wedge out on this side of the system here. And we have a shallower taper and a steeper taper. Places it's kind of broken up. You see here we have big depressions here or here or here. These are these normal faults. So if the transect happens to go across a big graben system, then we see sort of this destruction of the topography you'd like. So this one, for example, you can see some of these basins down here, for example, or if we go down into central Apennines, they're even stronger. So Florence, for example, sits in this is essentially a graben structure here. There's another graben up in here. So these are these sort of deep depressions, if you'd like, in the overall topography. The arrows at the top are just showing the GPS velocities. So again, this is showing relative to Europe. This is showing that everything is moving in this direction with respect to Europe, but we have extension again in the sort of the retro wedge side of the system. These arrows are moving faster than these. That means that this whole system at the surface is undergoing extension. So this is the kind of picture that we would construct for this kind of a system. And this again is our subducting system. This is our sort of orogenic belt in the sort of model that I showed you a few weeks ago, the typical sort of orogenic wedge system. The difference here being now that we have this extension going on back in the system back here. So compression in the front, extension in the back. We also have that extension actually goes all the way up in the shallow part, but the compression probably continues down into the deep part of the wedge. So our normal sort of ideas of orogenic wedges aren't really going to hold. And the kinematic pattern, deformation pattern, is also quite different. And I can show you what this looks like then in a very simple sort of kinematic model, just sort of in one dimension, not worrying about the deeper structures. But because we have this rollback of the slab, all right, so this is, here's the hinge, if you like, of the slab is moving to the right with respect to Europe. So this is in a Eurasian reference frame, which is indicated by these nails, if you'd like, here and here, right? So this is stable Europe, but the slab is retreating back in this direction with time, right? And that's leading to the compression here, but it also leads to extension back here. And so we're forming our sort of Tyrrhenian Sea, Western Mediterranean system, and here we're subducting the Adriatic system. And so we have to have shortening in the wedge and extension in the wedge back in this system here. So this is sort of forming an orogenic wedge. This orogenic wedge may well be a steady state wedge. You remember now our terms constructive, destructive, and steady. When I presented this before, this was all in terms of the mass balance between accretion and erosion. Here in this system now, at least in this little simple model, there's no erosion going on. There is erosion, of course, but even if we don't have erosion or don't consider the mass flux due to erosion, we can reach a steady state very easily in this system because we're losing mass by extension out the back in this system, right? So it comes in here, thickens up the crust, but then the crust thins again. And if it comes out more or less the same thickness that it went in, we can very quickly reach some kind of a steady state in this system. Right. I'm going to show you another little movie of another little sort of kinematic model here. Here's, in fact, exactly the same kinematic model. So this is just another view of exactly the same orogenic wedge system. We still have accretion on the right and extension on the back. The only thing that's changed now is the reference frame. So this is the same movie, but shown in a reference frame that's pinned to the hinge of the slab. So you see in this reference frame now, the slab doesn't move, but Corsica, which was over here, is moving out of the picture from right to left. So now Europe is moving and the hinge is fixed. So now what we see is the material is coming in. These are little marker pins, right? A material comes in, it's accreted, shortened, it comes into the orogenic wedge, and then it speeds up again as it leaves the wedge where the extension is occurring here, right? So this is a very different picture from a Taiwan or an alpine wedge where we really just see thickening and formation of the wedge, loss of mass by erosion. Here we're losing that mass also by extension. One more little geomorphic observation. These are the erosion rates that are observed. This is based on beryllium-10 data. So just looking at catchment-wide erosion rates, again, in the northern part of the Apenninic system. And what we can see is that they're relatively high erosion rates, relatively. None of the erosion rates are super high, but they're pretty reasonable, but they're higher on the pro-wedge side of the system than they are on the retro-wedge system. And we think the argument for this is that, in fact, most of the uplift is occurring on this part of the system where it's in contraction. Once we get into the high mountains and over onto this side, extension starts to take over. The surface is actually dropping by extension. And that means that erosion is not as active on this side as it is on the side that's uplifting. And finally, a little bit about the along strike variation. So much of the last talk has been focused on the northern Apennines. And the reason for this is that we think that the slab is rather broken up underneath the Apennines. So in fact, so here's the northern Apennines, central Apennines. We come down into Calabria, which is the toe of the boot. Sicily is over here. This slab system, which was fairly continuous along the whole length of the Apennines through much of the history, is beginning to run out of oceanic crust to subduct. So this part of the Adriatic is all thinned continental crust. We have true oceanic crust down in the south in the Ionian Sea here. But much of this, but at this point, in fact, really for the last few hundred kilometers of convergence has been taking down thinned continental crust. And we're clearly kind of running into the Dinarides in the near future. We're running out of sea out here. And we think in partially in response to that now, the slab is starting to break up and break off and start to sink. So if we image the slab underneath the system seismically, what we find is that it's just not very continuous. We have little pieces of it in the north. It's pretty good. We think we have pretty continuous slab through the north, but we come into the central region and there's nothing imaged. There is no slab left in this part of the system. Under Calabria, where it's oceanic, again, it's pretty continuous. Under Sicily, there's pretty much nothing, but it's kind of the edge of the system anyway, so we don't necessarily expect to find a slab. But the main point is that subduction to the south and north, but in the middle is maybe nothing. And interestingly, the central Apennines are the highest part of the mountain range, and they're also the region that has the highest rate of extension. Most of the earthquakes, the normal faulting is occurring in this part of the central Apenninic system. So the argument here is that in fact the slab has broken off. And if we look at sort of a cartoon version of the same thing, again, here's the Calabrian slab, here's the northern Apenninic slab, but in the central Apennines, there's nothing. So the slab is sort of broken off in this area. It's released that isostatic pull down. the whole central, maybe the southern Apennines are now popping up in response to this slab breakoff. It's accelerated the extension and largely shut off the convergence and the subduction. And this region is thus tectonically very different from regions either in the south or in the north. All right. So that's it. Thanks very much for your attention. This is the last lecture of the course. So this is it for us. It's been a pleasure, and have a nice holiday. Thanks.